So I'm super excited to be here today to talk to you about this new technology that we've built called Delta Lake, which, as he just said, helps you bring data reliability to your existing data lakes. But before I jump into that, first of all, who's familiar with this term data lake? Is this something everyone knows? Okay, most of the audience. I want to tell you a little bit about why people are excited about data lakes and why people have been spending millions of dollars setting up data lakes and trying to get insight from them. So the idea is this. You have a lot of data, and it comes in a wide variety of formats. It might be clickstream data, it might be metrics, it might be console logs, it might be structured SQL data, it might even be unstructured things like video and speech. And the magic of a data lake is you can store it all in one place. It's not a traditional database. You don't have to start by doing an expensive ETL process where you decide exactly what the right schema is. It's just a file system. So you can just dump everything there, and you can keep everything. And this is actually good because it costs something to spend all that time creating the schema, and you don't know what data is valuable a priori. Sometimes it's helpful to just keep everything and then look through it later. And the idea is once you've collected everything, in theory, you should be able to do data science and machine learning. So you should be able to build recommendation engines that will help people find the things they're looking for. You should be able to prevent fraud and decrease risk. Or you could even do crazy things like cure cancer using advanced genomics. But unfortunately, I have some bad news for you. It turns out that most likely, your data is garbage. And as a result, the data that you've stored is garbage, and you have this kind of standard problem of garbage in, garbage out. Your analyses are garbage as well. And why is that true? Why is it so hard to get high quality data inside the data lake? I want to walk through kind of a story that I've seen happen over and over and over again as people build together systems where they try to bring reliability to these data lakes. So this is kind of a pretty standard problem. My boss came to me and said, I've got a bunch of events. They're coming in through Kafka, but it could be Kinesis or S3 or Event Hub or any other system. And I have two missions. I want to do streaming analytics so I can understand what's happening in my business in real time right now. And I also want to do AI and reporting, where I take a more longitudinal look and I actually look at trends and make predictions about the future. So how are we going to do this? Well, I might be a little biased, but I would start by using Apache Spark. We have streaming APIs that allow you to read from sources like Kafka. You can do event time aggregation and all the other kinds of cool things you want to do, and you can get your streaming analytics. Great, we're done, right? Well, unfortunately, challenge number one is historical queries. Things like Kafka are great for providing a low latency buffer to bring data into your system. They're not great at storing all of the raw data for years and years and years of analysis. And so I read a lot of blog posts, I did a lot of thinking, and I came to this thing called the Lambda architecture, which, as far as I can tell, means we're just going to do everything twice. We'll have a streaming system that tells us what's happening now. We'll have this separate batch system that will archive everything. And then, once we set that up, it's one more thing to add to our architecture, but Spark has unified APIs for streaming and batch, so it's hopefully not too much work. And then we can do our AI and reporting. Great? Well, unfortunately, this brings us to challenge number two, which is messy data. As I mentioned before, most data is garbage. Someone upstream from you decided to change the format of the date without telling you, and now your parsing is wrong. And so we got to figure all of that out. And so I've seen a lot of people do this, and what they usually end up doing is they write a whole bunch more Spark programs, and those are going to do validation. They're going to check to make sure that the data that I expect is actually there, and if not, they're going to fire off some alarms so I can go and fix it. And since we Lambda architectured, I have to do this in two places. I have to do it in both streaming and batch, but unified APIs make it not too hard, so I can do that. We can add validations to the architecture, and we're good to go, right? Well, unfortunately, this brings us to mistakes and failures. I forgot to put a validation in, some bad data crept into my data lake, and that's difficult to fix. Because as we mentioned before, this isn't a database, it's just a file system. So going in and modifying the file system in place has all kinds of concerns. Can I even find the data that I need to change? What happens if I crash in the middle? Am I going to corrupt my data? And so I've seen another pattern here, which I bet many of you have actually probably implemented yourselves, where you're going to take your data lake and you're going to partition it. You'll break it up by day, hour, month, minute, whatever makes sense for your scale of data, and you'll build an engine that allows you to recompute individual partitions. So when something goes wrong, rather than reason about how to fix it, I'll just delete that day and recompute that day from scratch. And this is great, because now I can fix those mistakes that came into my data lake. This is one more thing to add to our complicated architecture, but with it, we can now have a little bit of certainty about what's actually going on. We can fix those mistakes. That unfortunately brings us to problem number 4, which is updates. reprocessing is great when you have one partition that needs to change, but what happens when something like GDPR happens? You actually need to scan through your entire data lake and allow somebody to be forgotten. Or if you want to do change data capture, as we heard about in the earlier presentation. I need to modify records all over the data lake very quickly, and that's very difficult. So you can build a whole nother set of Spark jobs that handle these updates and these merges, but you got to be very careful here, because if you modify the data lake while somebody's querying it, they're going to get the wrong answer. They're going to see partial results. Their analysis will be wrong. So you need to be very careful to schedule these at different times. I'm going to run my GDPR once a month at 3 in the morning. It better finish by the time the batch jobs start running, or my reports are going to be late. But it can be done. We can add that to our architecture, and now we have updates. But you're probably seeing a theme here. And to me, the problem is we're wasting a lot of time and money solving these well-known systems problems rather than doing what we really want to do, which is extract value from our data. And the distractions that are getting in your way and preventing you from getting that value out are a couple of different things. I think a big one here is the lack of atomicity. Atomicity means something either happens completely or not at all. And when you don't have it, anytime something crashes in the middle, which will happen in a distributed system, you have to reason about what happened and what didn't. How do I clean up from that failed state? And that's a lot of bug-ridden, tedious code to write. There's no quality enforcement. Nothing prevents anybody from dropping an extra file into that directory, whether or not it matches the schema that you're looking for. And that can make it very difficult to come back and look at it later. And then finally, there's no power for consistency or isolation, which makes it very difficult to do things like mix streaming and batch on the same data set, or query a data set while it's being updated. And these are all things that would be really nice. They would drastically simplify our architecture if we had these properties. So let's try it instead with Delta Lake. The idea here is we're going to take this relatively complicated architecture, and we're going to switch it to something like this, where rather than thinking about all these systems problems, we're only thinking about the flow of data through the system. And why are we able to do this? Well, I think one of the most powerful kind of techniques that we're going to bring to this problem is full ACID transactions. So this gives us atomicity, consistency, isolation, and durability. And this means that you can focus on your data flow rather than worrying about these intermittent failures. Delta Lake is, of course, open source and based on open standards. The data is encoded as Parquet. It's released under a full Apache license with no weird Commons Clause restrictions where you can't use it if I think you compete with me. And we actually recently joined the Linux Foundation to kind of create a permanent vendor-neutral home for this. So you can store petabytes of data without lock-in, which I think is really important. Data has gravity, data has inertia. If you're going to collect this stuff that is so valuable to your business, you don't want it to be in some black box format that's going to require an expensive ETL process to get it out if you ever decide to change things. You want to be able to query it with multiple engines. And as I'll talk about, we're working on adding support to other engines as well. But today, Delta Lake is deeply powered by Spark, which gives you the ability to work in both streaming and batch. And if you have existing Spark jobs, as I'll show in a couple slides, it's easy to convert your existing jobs with minimal modifications. So now let's simplify the picture. And I want to talk a little bit about some patterns that emerge once people stop thinking about these systems problems and start thinking about data. The first thing that I notice is people start thinking about incrementally improving the quality of the data until it's ready for consumption. And why is that? Why do you think about these things incrementally? Well, I see a couple of different classes of data that I'd like to talk about. So these are kind of high-level concepts. These are not baked into Delta. You do not have to have a single bronze, silver, and gold table. But I think these are useful ways to communicate with each other about the quality of your data sets. So starting off with bronze, we have our dumping ground for raw data. You often keep years of data here, and you might say, wait a second, why am I storing this raw data? Well, there's a couple of reasons for that. And I think the most interesting one is there are no bugs in a parser that you don't write. If you just store the raw data, you can always go back to it and reprocess it from the beginning of time. And Delta is designed to store years and years of data in a single place. Moving on from there, we have our silver tables. These are cleaned up a little bit. You've maybe joined, filtered, aggregated them. You've taken some JSON data and parsed it out to top-level columns. This is intermediate data sets where you've done some cleaning, but it's not quite ready for consumption. And you might say, wait a second, why am I wasting the time materializing these intermediate data sets? I think there's actually a couple of interesting reasons. Number one is you're probably not the only person in your organization who will find value from this partially clean data. And by materializing it as a table, this is a great point to fork off and allow everyone to kind of benefit from the cleaning that you've done. But another reason is, which I actually was kind of surprised by, debugging. When you get to your final analysis and something is wrong, having that intermediate data set as a fully materialized table that can be queried with the full power of SQL means that you can actually figure things out about where things started to go wrong. You can check and see, wait, how many times is this column null? Or how many distinct values are here in this intermediate step? And that makes it dramatically easier to understand what's going on. And then finally, we have gold data. These are high-level business aggregates that mean something to somebody important. You can power your reports. You can do AI on it. This is clean data that's ready for consumption. And you can read this with Spark, and we're kind of extending this to work with the Presto community as well. We're currently working with Starburst on that. Another pattern I see is a lot of people switch to use streaming. And I want to talk a little bit about this because I think streaming, there's some misconceptions about what it's for. A lot of people think that streaming is an extra complex thing that you do when you need hyper low latency things for some reason. And to me, that's one thing you can do with streaming, but that's missing the power. Streaming to me is about incremental computation. It's this problem where I have this transformation that I want to do, and my data set is continually changing. That's pretty much everything we do with data. Nobody has a static data set. And what the streaming engine does is it allows you to kind of stop thinking about these problems of what data is new, what data is old, how do I incrementally process the new data and move it downstream, how do I transactionally commit it, guaranteeing exactly one semantics, how do I checkpoint where I'm at so I can recover from failures. Streaming takes care of all of this for you. And there is in Spark a very nice kind of cost latency trade-off that you can kind of make automatically. If you do really care about hyper low latency millisecond processing, you can run in continuous mode. And we will hold on to a core and continually poll Kafka and give you hyper low latencies. If you care about seconds to minutes of latency, you can use micro-batch processing, where we will run many different streams on the same cluster, each taking tiny little epochs of time on each of your executors. And finally, if you have a data set where data only arrives once a week, don't keep that cluster running all the time, use trigger once. In trigger once, the system will boot up, process everything that is there, and then if you're running in the cloud, shut down. It's an amazing way to take advantage of the elasticity of the cloud while still getting the benefits of streaming. You can save a lot of money by turning your cluster off when you're not using it. Now, of course, streaming is great, but batch jobs happen. And there are a lot of reasons why you might need to run batch jobs as well. So I mentioned GDPR. Once every month, you might want to sweep your data lake for anyone who sent you a DSR. You might have retention requirements where you only want to keep the last 2 years of data and then remove it. Or you might kind of want to do upserts so you can do change data capture from some operational data store. And Delta Lake supports all of these on the same data sets that you're streaming to and from. Another pattern that I'll note is recomputation. If you follow all of this stuff, it's very easy to, when you have a new analysis that you want to do, or when you notice a mistake in your existing analyses, recompute from the beginning of time. So the reason that this is so easy is because a stream in Apache Spark actually computes the same answer as a batch job over the same data set. So when you start a new stream, what it's going to do is it's going to take a snapshot of the table at that moment, break that up into pieces, process them incrementally, and then when it gets to the end of that snapshot, it will start tailing the transaction log and incrementally processing new things that have arrived since the stream started. So when you find a mistake, it's as easy as clearing out that table, creating a new checkpoint, and running the stream from the beginning of time. And it'll automatically kind of scale out and use a whole bunch of machines early on, and then when you get down to that incremental processing, you can scale that cluster down to something significantly smaller. So next I want to talk about who's actually using this. And before we released this as an open source project, Delta was a kind of, for the last 2 years, proprietary product inside of Databricks. It's used by thousands of customers around the world, and I actually need to update this slide. We processed over 2 exabytes of data last month. I want to talk about one particular use case, though, that I found pretty exciting. This is Comcast. They use it for sessionization. So they have this problem where there are, millions of people around the United States clicking with their remotes, going through from the home shopping network to HGTV back to the home shopping network, and they want to figure out what is that content journey like. They want to understand how people are consuming their content. They've been doing this with Apache Spark for years, but they have this problem. There's too many subscribers. And so the scheduler would just tip over if they tried to run this on a single cluster. And so, being good engineers, we know how to solve scale problems. We'll use hash partitioning. So what they had to do was they had to take this job, split it into 10 different jobs, running on 10 different clusters with 10 different schedules, 10 different sets of logs, 10 different sets of errors to handle and manage. But they were able to get it to work. However, when they converted this to Delta, because of our scalable metadata handling and because of kind of our efficient use of transactions, they were able to collapse this down into one single job. And that actually has huge implications for their productivity. When you're managing one thing, that's much easier than managing 10. And they also reduced the number of machines that they needed by 10x as well, which is a dramatic reduction in cost. So now they have all of this extra money to do other cool, different analyses rather than wasting it all on this one. So how do you use it? It's pretty easy to get started. It's published out on Maven. If you're already using Spark, all you need to do is add this one command line argument. It'll automatically download and install Delta on your cluster. If you're using Maven or SBT, the coordinates are up there. You can add it to your project. And in terms of code, it's actually also very easy. If you're using the data frame reader and writer, all you need to change is from Parquet or CSV or JSON, whatever you're using today, to Delta. And everything will work as it did before, except now you have ACID transactions. I want to give you just a preview of some stuff that we're working on as well. This is kind of a project that's underway that we're hoping to open source in the next couple of months. But the idea here is transactions are great for making sure that your code runs correctly, but it doesn't prevent you from having bugs in your code. In order to do that, we need something a little bit more. And the idea here of Delta pipelines is we're going to give you the ability to declaratively specify your entire production ETL graph as one single entity. And this actually makes it very powerful. So looking here, I'm creating this thing called a data set. I'm using the kind of familiar APIs I already know and love from Apache Spark, just data frames, data sets, Scala, Java, Python, or even just pure SQL. I can declaratively specify where it should be stored, what requirements there are on the schema, whether or not it should be registered in a metastore so that other people can discover it. And I think this is actually also very powerful. I want to talk a little bit about the schema in particular. Delta has kind of tunable ability to make the schema very strict. In kind of your bronze tables, I will often see people use automatic schema evolution. So Delta will just automatically add any new columns, assuming there aren't conflicting data types as they arrive. But you can also act more like a traditional relational database and say, nope, anytime the schema changes, I want somebody to run alter table and do strict DDL. It's more common in the bronze or in the gold data sets. But my favorite feature is this thing called expectations. Expectations allow you to take your domain knowledge about what correctness means and actually put them into the system. For those of you coming from a traditional relational database, this sounds a lot like invariance, but with a key difference. An invariant will kind of fail the transaction anytime something goes wrong. And with expectations, we can actually have tunable severity. So in this case, I'm defining this expectation that there's a valid timestamp. And it's actually more than the timestamp just being present. I know that Databricks started in 2012. And so if a record appears from, say, 1970, that is probably a misparse and not actually a valid date. And so I'm kind of putting that domain knowledge into the system. And then I can choose what to do when that expectation is violated. If this is a final table that I report to the IRS, I probably do want to fail that transaction, make sure no bad data ever makes it in there. However, if it's an earlier table, perhaps I just want to monitor the quality. So I want to alert if it goes above 5%. Or my favorite is a quarantine. So anytime an unexpected record is seen, rather than shut everything down, we allow processing to continue, and we take that unexpected record and route it to a quarantine table where an engineer can come and look at it later. So this allows you to continue processing your data while still understanding what's actually going on under the covers. I've been using this on my own data sets, and it's amazing what you find, because in many cases, your expectations are wrong. As we talked about before, your data is garbage, and we tie deeply into Apache Spark. So we'll actually modify the query plan so we can say things like, here was the input record, here was the output record, here was the expectation that was violated, here was the code that produced that invalid record. It makes it much easier to understand what's going on under the covers. So finally, I want to talk a little bit about how this actually works under the covers. I want to kind of deep dive into the nitty-gritty details because ACID transactions in a distributed system sound too good to be true in some cases. So starting off with how, the kind of file format for Delta. Delta on disk will look very familiar to any of you who already have a data lake. It's just a collection of Parquet files in a bunch of directories. But we add to this a transaction log. And the transaction log stores different versions of the table. So here we have version 0 and version 1 of the table, alongside these kind of optional partition directories and data files. Now, a version is defined as the set of changes from the previous version. So what kinds of changes are we talking about? Well, you could change the metadata. So if you, for example, add a column to the table or change the partitioning of a table, you can add data to it. So we do this at the file granularity. So you can add a file along with optional statistics like min and max values for each column that allow us to do really cool tricks like data skipping. And then finally, you can remove data from the table. So you can remove a file from the table. And if you think about this, you can now take the transaction log from the beginning of time and play it. And when you get to a specific version, what you will have is the current metadata for the table and a list of the files that are currently in the table. So we're using a trick here called multi-version concurrency control. Many copies of your data live together in the same directory, but this is the authoritative source for which files are valid at any given version. Now, we want to get those really nice ACID properties on top of this. So how do we get atomicity? Well, we're going to basically take each of these individual units, these kind of delta files, and we're going to use the atomic primitives of the underlying file system to create them. So if you're storing this on S3, puts to S3 are atomic by definition. The way they get this is when you start the put, you say expect this many bytes. And unless they get that many bytes, the put doesn't go through. So you get atomicity kind of out of the box. On other file systems like Azure Data Lake or HDFS, we'll just use atomic rename. So we'll create a temporary file and then move it to its final destination. That way you'll never get a partial file. So in this case, we've added 2 files, and let's say we want to atomically compact them. We want to take them and collapse them down into a single file. Well, we can do that. If we didn't have atomicity here, we'd be in a really bad space, because if we deleted those files without creating the third, we would have lost data. If we added the third without deleting them, we would have duplicated data. Either of those would be bad for our data quality. And so this atomicity is actually very powerful. The next thing we want is serializability. We want everybody to agree on the order of changes so that we can kind of have a consistent view of the data at all times, even though there's multiple people modifying it. So here, I want a property called mutual exclusion. If one user creates version 0, great. If another user creates version 1, that's awesome. But if 2 users try to create version 2 at the same time, one of them needs to fail. And again, on S3, this is actually impossible. It is not a lock service. So you can have kind of another database that mediates who the winner is that does give you this property. On things like HDFS and Azure Data Lake, their rename operation actually can fail if the destination already exists. And so you kind of get this property out of the box. Now, you might be saying, wait a second. If every time 2 people modify the table at the same time, it crashes, well, that's not very great for me as a user, right? I thought this was going to make my problems easier. Well, fortunately, we have one more trick up our sleeve, which is called optimistic concurrency control. So we're going to optimistically do these as though nobody else is modifying it, and then we're going to check for conflicts among these operations. And in many cases, there will be no conflicts, and we can move on. The algorithm is as follows. So let's say there's 2 users who are both streaming into the same table. So they record the start version. So they say, OK, I am streaming in starting at version 0 of the table. They record what they read from the table and also what they write to the table. So in this case, the only thing they need to read from the table is the schema. They need to validate that the data that they're writing in matches the schema of the table. And then they're both going to attempt to commit. So they'll say, OK, I wrote out all these files, and now I want to add them to the table. In this case, user 1 wins, and user 2 loses. And so what user 2 is going to do is they're going to check and see, hey, did anything that I care about change? And in this case, the only thing they saw was the schema. The schema did not change. And so we can just lie to them and say, actually, you came afterwards. And they don't know the difference. And so we kind of automatically run this transaction again. Nobody notices that there was a conflict. Things continue on automatically. We have one final trick up our sleeve, which is in a data lake, you can get really massive collections of data. I've seen a couple that have millions to tens of millions of files in them. And so at this point, the metadata of the table actually starts to become a big data problem in itself. How are we going to solve that? Well, fortunately, we have a big data system, Spark. So what we're going to do is we're going to design the transaction log in such a way that it also can be processed by Spark. So we'll take all of these actions, we'll load them into Spark, and we'll do a shuffle, we'll resolve them so we have only the current set of files, and then we'll create a checkpoint, which we actually also store as Parquet, this nice efficient columnar format. So now, when you want to query the table, rather than replay the log from the beginning of time or make a lot of really slow metadata calls to S3 to figure out which files are there, you can actually just go directly to this checkpoint. And you can even do things like say, this table may have tens of millions of files in it, but I only care about yesterday. So you'll run a really quick distributed query to identify the files that are relevant to yesterday, and then you'll run another query over the file set that is returned. And this allows you to scale much further than you would if you were storing this in something like MySQL or the Hive Metastore. I think anybody who's tried to put tens of thousands of partitions in the Hive metastore has kind of felt that pain. So finally, I want to talk a little bit about the roadmap for the project. As I said before, this is a relatively young open source project, but my goal is to have full API parity by the end of the year. So that has actually been the last couple of quarters of work. We added support for S3 and Azure Blob Store. We added the ability to do all these cool DML operations, update, delete, merge. We added the ability to convert existing Parquet data into Delta and do describe history. And with Spark 3.0, we'll have kind of full support for DDL, the create table, alter table, and all of those kinds of things. So with that, I'd like to encourage you to head over to our website, delta.io, join the Slack channel. We hang out there all the time. We'd love to answer questions, join the mailing list, fork us on GitHub. Thank you very much.
Great. Any questions for Michael?
So can you discuss the challenges of implementing additional data file formats? You mentioned Parquet. Is it easy to just also support Avro?
Yeah, that is a great question. So we actually just published the protocol spec up on GitHub, and there's a section on that. We actually already support any file format that Spark supports. Now, there is some interesting, it is not exposed to users, and I would love to talk to more people about this because we're very open to changing this. But when you're designing a system or a product, I like to kind of think about how can I remove tuning knobs. And so we picked Parquet because we know it's fast with Spark. We know it's kind of pretty optimized there. And I've actually had a couple of customers where they took their existing data that they were storing in something like Hive sequence input format, and they converted it to Delta. They did no other tricks. They didn't do compaction. They weren't taking advantage of ACID transactions, nothing else. But their queries went from taking hours to taking minutes. And they were like, oh man, Delta's awesome. And I was like, oh, actually, I just forced you to use a reasonable file format. Now, you asked about Avro. I think there actually are interesting differences between Parquet and Avro, where Avro might make sense. So yeah, please go to GitHub, tell us what you're trying to do, and I'm more than happy to kind of open up extra knobs, if they're useful. Any other questions? Yes.
Hi. I've learned a bit about Iceberg for the first time in the past couple of days. Do you have any sort of compare and contrast?
Yeah, absolutely. Right, so, just for those of you who don't know, Iceberg is an Apache project. I actually know Ryan Blue pretty well. He's one of the creators of it. I think, in design, Iceberg and Delta are actually pretty similar. So, I think if you're going to try to build ACID transactions on top of cloud storage systems, the design most people have come to is you'll have a separate place for tracking metadata at the file level rather than at the partition level. We kind of all have this. So I think, in that level, they're very similar. I think where they differ, Iceberg has a couple of features that I'm really excited to copy. In particular, I think computed partitions are really interesting. And also they have the slightly better ability to rename columns through an extra level of indirection they have. Now, the difference with Delta, though, is I think Delta has full support for streaming, which I think is critical to running data pipelines at scale. We have update, delete, and merge. And I think the kind of primary difference to me is Delta is in use by thousands of organizations around the world in production and has been for 2 years. We store multiple petabytes of data. We process exabytes per month. Iceberg is a relatively young project.
Any more questions?
Hi, you mentioned that when you're trying to consume from data lake, you can enable it for the ultra low latency by enable pulling from Kafka all the time. So does the Spark streaming really guarantee that it's a per message processing, or it's essential per message processing similar with the Kafka stream, or it essentially is still a macro batch?
Yeah, great question. Okay, so first let me clarify. I'm going to put my Apache Spark hat on, and then I'll answer for Delta Lake next. So yes, Spark continuous processing is true streaming. It sits there, holds on to the core, pulls from Kafka, supports millisecond latency. Do not listen to the FUD that says Spark is only microbatch. That has not been true for 2 years. Now, Delta. Where is Delta's sweet spot? Delta is about creating bulky Parquet files that you store on a system like S3. We're not talking milliseconds anymore. Round trips to S3 are like 500 milliseconds already. The sweet spot for Delta is seconds to minutes.
Any other questions? There was one gentleman back
right
here, I thought. No?
There's one right here.
Hi. So the colors that you showed, like there's bronze, gold, silver. So that's part of the API, or is the internal implementation detail that people don't see?
Yeah, that's a great question. Bronze, silver, gold, is that part of Delta? No. Here's what that is. That's a common misconception. So there's nothing in the Delta API that enforces bronze, silver, and gold, but that is a pattern that I notice that people get into once they stop thinking about systems problems and start thinking about data quality instead. So that is just a very useful vocabulary that I have seen evolve. You can not use it. You can have 10 bronze tables and skip directly to gold. It's all up to you. And with that, I think we're at time. So thank you very much.
That's all we have time for. Thank you very much, Michael. Appreciate it. Next talk begins in 9 minutes, 30 seconds.